Now, I expect that you're fairly familiar with the properties of conductors and insulators from both Physics 1B and from high school as well. So we're just going to briefly cover some of the basic properties of a conductor. One of the interesting properties is that inside a conductor, the electric field is equal to 0. And let's have a think about why that is. Well, charges are free to move inside a conductor. So let's imagine that we have something which is conducting here, and we have a charge here which is free to move. Now, if there is an electric field, let's make this one here a positive charge, and we have, say, an electric field which is pointing up like that. Well, this positive charge is going to experience this electric field and move as a result of it, and so it will move up the top here. Because it can't move outside because it's still stuck within the conductor, but it's free to move within the conductor. But then once it's up there, well, it's always generating its own electric field. So it's now got electric field lines going down like that. It'll have electric field lines going in all these directions. But there's lots of these charges which are free to move. So if we continue applying this electric field like this on the conductor, say it was coming in from outside like this, then the charges inside the conductor are going to keep moving up here until they are generating their own electric field down like this, which has the same magnitude as the upwards one, because the electric field describes the net force which is going to be felt by each of those charged particles. Well, it's proportional to the charge times the electric field gives us the force. And so when these two balance, there's then no net force. So then the additional charges stop moving up here, in which point we've reached an equilibrium where these electric fields are cancelling each other out, which just goes to show our point that there is no electric field inside a conductor. So the charges move very quickly inside a conductor, and this condition is met relatively instantaneously. Okay, now a property that follows on from this is that the charge density is equal to 0 inside a conductor as well. And this just follows on from Gauss's law, which tells us that the divergence of the electric field is equal to rho over epsilon naught. But because there is no electric field inside a conductor, this thing's 0, it tells us that rho must also be equal to 0 inside that conductor. Another point is, like as we discussed, these charges moved up the top, so to the surface. They moved as far as they could, and where they got stopped was at the surface. So this tells us that any net charge resides on the surface of a conductor. Okay, another point is that a conductor is an equipotential. And again, this comes about because the electric field is equal to 0 within the conductor. So we know that the potential difference between A and B, well, let's call it VA minus VB, is equal to minus the integral from A to B of E dot dl. And because E here is 0, this is equal to 0, which tells us that VA must be equal to VB. So, i.e. 2 points, A and B, inside the conductor, so say here A and B, they must be at the same potential because there is no electric field between those points. And finally, we've got that the electric field is perpendicular to the surface. And this is outside the conductor because there is no electric field inside the surface. So, for example, on this one up the top, we had that this had electric field lines going out like that or perpendicular to that surface. And whatever odd-shaped surface we have, the electric field lines are perpendicular to that surface. They're always at right angles to it. And this has to be the case because if we had a tangential component, then one of the charges inside the surface would be able to move to cancel that out, but they can't cancel out the components which are perpendicular to the surface. So basically the charges all spread themselves out as much as they can over the surface of the conductor to ensure that the electric field inside is equal to 0. Okay, so now we're going to consider some of the implications of the electric field inside a conductor being 0. So we're going to be looking at induced charges and what happens when we have cavities inside conductors as well. So I actually find this part quite fun. So let's consider if we had some conductor over here. So this is our conductor. And then we bring a charged sphere close to it. So we'll have this one here is a charged sphere. Well, what happens is we know that inside this conductor, the electric field is equal to 0. So as we've just discussed, the charges inside the conductor are going to have to kind of rearrange. So if we draw the electric field lines coming out of this sphere here, they're coming out like this. I mean, they come out in all directions, but what we care about is what happens near the conductor. And so the charges inside the conductor are going to rearrange around here and around here to cancel out these electric field. So let's say that this is an uncharged conductor for now. Let's make it uncharged. And then let's draw how these charges are going to redistribute. Here we're going to get negative charges concentrating here because this is uncharged. This negative charge will be obtained by electrons moving over here, which will leave some positive ions behind, the same number of single positive charges as we have negative charges, because overall it's neutral. And so this is going to create an electric field around here, which is going in this direction to cancel out this applied electric field here. So we get induced charges in conductors when we bring a charged particle near it. Now, let's consider what happens if we have a cavity inside a conductor. So let's take this kind of similar conductor, and then let's put some odd cavity shape in it, and let's put a positive charge in here, so plus Q in there. Now, Gauss's, we know that there is no electric field inside a conductor. And Gauss's law tells us that if we take a Gaussian surface like this, so say this is a sphere that contains the entire cavity there, in that case we know that E dot dA is equal to Q enclosed over epsilon naught, and E, we've said inside the conductor is 0, so we've got 0 is equal to Q enclosed over epsilon naught. So that tells us that there must be a charge around the surface of this cavity here to cancel out that positive Q charge there. So on this surface, we'll have a charge of negative Q distributed, but then because this entire conductor is uncharged, we're still assuming that it's an uncharged conductor, so uncharged conductor. the net charge must be 0. So if we have a negative charge of negative Q on this surface, we must then have a charge of positive Q on this surface. So charge of plus Q on this surface. So you have seen some problems like this in Physics 1B, but let's have a look. Let's solve another problem making use of this now. So in this problem, we have a metal sphere of radius r. So let's just sketch this out as we go. Here's our metal sphere with radius r, and it's got a charge q. And it's surrounded by a thick concentric metal sphere with inner radius a. So this here is a, and outer radius b. So this radius here is b. And these are all made of metal, which means that they're all conductors. So the shell carries no net charge. And part A asks us to find the surface charge density at R, at A, and at B. Okay, well, we know that for a conductor, all the charge is on the outside because any Gaussian surface inside contains no charge because there is no electric field. So that tells us that for this inner sphere here, all this charge Q is spread over this surface. So we can use that to calculate the surface charge density, which is just the total charge divided by the total surface area, which is 4 pi r squared in this case. So that is the charge density at R. Next, we need to calculate the charge density at A. Now, let's think about what's going on. We know that because this is another cylinder, a cylindrical shell, inside this metal spherical shell here, there is no electric field. So, for example, with the green Gaussian surface that I have drawn there, that must contain 0 charge. So because it contains a charge Q from the inner sphere, it must contain a charge negative Q on this surface at radius A. So there must be charge minus Q at radius A. So we can use that to calculate the surface charge density. It's just the total charge, which is negative Q, divided by the surface area, and this is a sphere again, it's a spherical shell, so that is divided by 4 pi A squared. And then we need to work out the charge density at B. And we know that the shell carries no net charge. So because it carries no net charge, if it's got a charge of minus Q on this surface, it must have a charge of plus Q on here. So it must be charge plus Q at radius B to cancel charge at A. So we can use that to calculate the surface charge density there. It's going to be a charge plus Q divided by the surface area, which again, it's a sphere, so that'll be 4 pi B squared. Okay, so part B says find the potential at the center using infinity as the reference point. Okay, so let's change colors for this and let's consider what we're doing. So we've got out here at R is equal to infinity, our voltage is equal to 0. That's what it means when it says I'm using infinity as the reference point. And we are trying to find the voltage in the center of the sphere here at little r equals 0. So what we're going to need to do is consider this path between these two, because we know that the voltage is equal to minus the integral over this path. So we're going from r equals infinity to r equals 0 of E dot dl. Now, what we're going to do is we're going to consider each little bit of the path separately because the electric field is actually different for the different bits. So here there'll be an electric field. Inside the conductor, there is no electric field. Here there's an electric field again, and then inside the conductor here, there's no electric field again. But let's write all of this out very explicitly, just so that everybody's really clear on it. Okay, so we are going to start with this path. We're going from infinity to radius b. So we express that as going from infinity to radius b. And then we need to think about what the electric field is going to be in this region here. So to do that, let's consider this Gaussian surface like this. And because it's got a charge plus q and minus q there, those cancel out and we've just got charge q there. So we know that E dot dA here is equal to q over epsilon naught, and the surface area here is given by 4 pi r squared. So hopefully you can see that that means that the electric field in this region is going to be given by q over 4 pi epsilon naught times 1 on r squared dr. Okay, so we're at here. Now we need to do this next bit going from b to a. So this will be minus the integral from b to a. And for that part, we're inside a conductor. So the electric field is 0. And then what we'll want to do is we'll want to go from a to capital R. So this will be minus, well, let's put it on the next line. So minus the integral from A to R, and we've got another Gaussian surface here, which also has an enclosed charge Q. So the expression for the electric field is actually the same as above. And then we need to go from the surface of this sphere to the center here. So then we've got minus the integral from R to 0, and the electric field is 0 there because we are inside a conductor. Okay, so two parts of this integral are going to be 0 because we're just integrating over 0. So let's do the rest of this integral. So with this first term, we can pull q over 4 pi out the front, negative, and then we're integrating 1 on r squared. So that'll give us minus 1 on r, and we're going from infinity to b. And this is the same integral. So this will be minus q over 4 pi epsilon naught, but we've got different limits here. So this is minus 1 on r, but now we're going from r to a. So let's substitute in our limits. You see how we've got double negatives everywhere. So let's just make everything a plus. And then we end up with q over 4 pi epsilon naught. That's a common factor. Here we've got 1 on b minus 1 on infinity. And then we've got plus 1 on r minus 1 on a. And 1 divided by infinity, that's going to give us 0. Okay, so we can write this as equal to q over 4 pi epsilon naught, 1 on b plus 1 on r minus 1 on a. So that is our expression for the potential at the center. Okay, we're running out of space, but part C says now the outer surface is touched to a grounding wire, which lowers its potential to 0, same as infinity. How does your answer to A and B change? Okay, so when we touch this surface here to Earth, it gets rid of this charge plus Q here. So now what we have is a charge Q on the inner sphere that's not touched to ground, so that doesn't change. Inside this conductor, we've still got 0 electric field. That doesn't change. So we've still got the charge minus Q there. That still holds. But now that this has been touched to ground, we're removing this requirement that the shell carries no net charge. So at this point, We've still got zero electric field here, but we now have no charge here. That's drained down to ground. So this part here is now wrong for part C. The charge at B is 0. So for part C, this one remains the same, this one remains the same, but this one becomes sigma B is equal to 0 just because there is no net charge. Okay, and then we're asked to calculate how the voltage changes as well. So, I mean, working our way out, this part remains the same. There's still no electric field inside the conductor. Now we've still got the charge Q at radius R, so this second part is going to remain the same as well. Between A and B is still inside the conductor, so that part remains the same as well. But what this part here is now different because we came up with that by considering this green Gaussian surface here. But now the enclosed charge is 0 because we've got Q here and we've got minus Q here, but we don't have anything there. So the total charge inside here is 0. So this one here becomes 0. And so that tells us that the only part which is contributing is this part here. And so our expression for the voltage for this part is going to be just this part here, which is Q over 4 pi epsilon naught 1 on R minus 1 on A. So that's our answer to part C. So we're now going to be considering the electric field at the surface of a conductor and using that to derive some useful equations about the force and the pressure on charges in the surface of a conductor. So the picture I want you to have in your mind is the surface of a conductor like this. So below the surface, we've got the conductor where there is no electric field. Above the surface, we've got a region with the electric field due to the surface charge density on this conductor. So remember, with a conductor, all the charges are on the surface. Now, before, when we were discussing boundary conditions for a sheet of charge, I've sketched a kind of copy of the little figure that we had here, and I've copied this from the notes on boundary conditions. We derived the equation that the electric field above minus the electric field below, and I've written above here and below here, is given by sigma on epsilon naught times the normal force. So in this case here, we've got an electric field going up due to the surface and also coming out down here. Both of those are at a normal to the surface. So now if we apply this expression to this condition here, below the surface, we've got no electric field because this is a conductor. So substituting into that, we can write, well, E above minus E below is equal to E above minus 0, which is equal to sigma over epsilon naught n. So this tells us that for a conductor, the electric field is equal to sigma over epsilon naught n. And so this is an electric field which is perpendicular to the surface of that conductor like that. So that's one useful equation that we'll be using. Now, it's useful to also remember that the electric field is equal to the gradient of the voltage. So this lets us come up with an expression for the voltage because the only component of the electric field that contributes is the normal component. So we can write, well, sigma over epsilon naught is equal to minus dv dn. Or we could write this, if we want, as sigma is equal to epsilon naught, well, minus dv dn. So those will be useful equations later. Now, what we wanted to think about was the force on a conductor. So what we want to think about is if we had a little patch of a surface, like this little patch here, I've drawn a little patch on the surface. So we want to kind of ask, what's the force on this little patch of surface due to the electric fields around the surface? We had at the very start F is equal to QE. That's how we get between the force and the electric field. So let's write this as F is equal to sigma E, where lowercase f here is the force per unit area. And sigma here, that's the charge per unit area because it's the surface charge density. The problem with this is, what do we mean by the electric field E here? Because we've said that the electric field is discontinuous at the boundary. So do we mean above? Do we mean below? Well, it turns out that what we actually mean is the average, but let's show why that makes sense by considering this case over here where it's not necessarily a conductor. We'll just go back to our old example here, and I've drawn a little patch in this surface as well, and we can say that the electric field on this patch here comes from two components. We've got the electric field which comes from the patch itself because it has its own charge and it's creating its own electric field. And then we can sum up the contribution of the electric fields from everything else, so from all the rest of the surface like this. So we can call this plus E other. Now, hopefully you'll remember from mechanics that internal forces, so forces which are acting upon the body which is applying the force, don't actually count. They can't actually change the motion or make anything happen. So how Griffiths describes this is now the patch cannot exert a force on itself any more than you can lift yourself by standing in the basket and pulling up on the handles. So the electric force of the patch on itself is an internal force, and it doesn't contribute to the net force that we consider when solving problems. Okay, so let's have a think about how we can express E other here. So once again, we'll consider two parts. We'll consider the electric field above this plane here, and we'll consider the electric field below this plane here. So above, we've got the electric field from the charges going up, and down below, the electric field from this sheet of charge is going down. So let's write down our expressions for that. We've got E above is equal to E other, because this sheet of charge isn't necessarily the only electric field here. There could also be an additional external electric field. This E other contains any external electric field plus all the electric field from the components of the rest of the sheet, which I've kind of colored in green there. And then we've got, plus we've got sigma over 2 epsilon naught n. So notice that this is half this, because the difference between them is like sigma over epsilon naught. So we've got upwards, we've got sigma over 2 epsilon naught, and downwards we've got sigma over 2 epsilon naught, and that gives the difference of sigma epsilon naught between those two. And E down is equal to E other, and this is acting in the opposite direction to this now. So using these two expressions here, if we sum these together, we can come up with an expression for E other. So we've got E above plus E, well, I should have said below, not down. Sorry, that's below. Below is equal to 2E other, which tells us that E other is equal to a half E above plus E below. So this is telling us that the other electric field, so the external and any contributions from the rest of the sheet, are equal to the average of the electric field above and below, which was what we were trying to get to for this. So this one here is that other E, so the average E. So this tells us that the force per unit area should be equal to sigma times E average. Okay, and now we are considering this situation again, where above we've just said that we've got this electric field, and below we've got zero electric field because we're inside the conductor. So this tells us that for the case of the conductor, we've got that this is equal to sigma times a half times sigma over epsilon naught n. So this is equal to sigma squared, because we've got sigma times sigma, divided by 2 epsilon naught n. So that is the force per unit area on a part of the surface. And we can actually express this also as an electrostatic pressure, because hopefully you remember from physics 1A that pressure is equal to force divided by the area. And this is just the force per unit area, but pressure, remember, is a scalar. So all we need to do there is get rid of our vector. So this tells us, let me just move this up a little bit so that we've got a little bit more room, that the pressure is equal to sigma squared over 2 epsilon naught. But if we want to substitute in with E squared, this is taking the E above. It's taking this E here. So we can say, well, E squared is equal to sigma squared over epsilon naught squared. This is above. And so we can write that this tells us that P is equal to epsilon naught on 2 times E squared, where E here means the electric field above the surface. So this gives us the electrostatic pressure, and this is called electrostatic pressure. So these equations will come up in the future, which was why it was important to derive them. Okay, so now we're going to be considering capacitors. Hopefully you remember quite a lot about capacitors from Physics 1B. So a capacitor consists of two conducting charged things. So they can be plates like this, they could be spheres like this, they can really be any shapes we want, but we have to have conductors which are separated and contain a charge plus Q and a charge minus Q. Now, because these are conducting plates or conducting shapes, they've got a constant voltage over the entire area. So this is at one voltage, this is at another voltage, and we can define the voltage difference between this top plate and this bottom plate using that the voltage difference is equal to the voltage of the positive plate minus the voltage of the negative plate. And that's always going to be a positive number. And if we knew the electric field in between, we could use our equation that the voltage is equal to the integral of E dot dl in order to calculate that voltage. So in this case, to get the voltage between these two plates, we're going to take our path from this negative plate to the upper plate. So that's my limits on my integral here. This is the place at the bottom plate. This is the place at the top plate. And that gives me my voltage difference between these two plates. Now, electric field is proportional to the amount of charge. Coulomb's law tells us so one way we can write Coulomb's law is 1 over 4 pi epsilon naught times the integral of rho over curly r squared times r hat dv or d tau. And so if we double Q, then we're going to be effectively doubling the volume charge density. We're doubling the number of charges in the volume, so we double this, and that doubles the electric field. So the electric field is proportional to the amount of charge. So E is proportional to Q. And so since E is proportional to Q, if we increase this by a constant, this increases by the same constant. So that tells us that V is also proportional to Q, which is really where the capacitance comes in, because the capacitance is effectively the proportionality constant. So how we define the capacitance is the capacitance is equal to Q over V, and so it is the proportionality constant. Now, capacitance obviously depends upon the shapes of our arrangements. So these rectangular plates are going to have a different capacitance to these spheres like this. It'll depend upon the geometric arrangement, so the distance between them. It'll depend upon the sizes of the two conductors, and it's measured in units of farads, which have a symbol capital F, and that is equal to coulombs over volts, just because we've got a charge divided by voltage. So let's have a look at how we could calculate the capacitance for a very simple case. Let's consider this setup here, where we've got a parallel plate capacitor. Let's let both of these have surface area A, and we'll separate them by a distance D. Now, quite a few times we have calculated what the electric field is from a sheet of charge. Just to jog your memory, this is the latest place where we used it. We said that with a sheet of charge like this, we had a electric field of sigma over 2 epsilon naught coming up on this side, and an electric field of sigma minus 2 epsilon naught going down on the other side. So let's sketch that on here. From coming out of this positive plate, we've got sigma over 2 epsilon naught going that way, and because this is a negative charge, the electric field is going into this plate here, so it's going into here, so that's sigma over 2 epsilon naught, and those are in the same direction. So the electric field between these two plates is the sum of these two things, and they're both in the same direction, so that's sigma over epsilon naught, and it's downwards. Okay, so if we want to calculate the voltage between those two plates, we can use that this is equal to negative E dot dL. So we're going from the lower plate. So let's say that this lower plate is at 0, and then this upper plate is at D. So we will go from 0 to D. And E in this case is downwards. So that is minus sigma over epsilon naught. And this is times, should we call it dr? It doesn't matter. It's this path upwards that we're following. That in this case, r describes the distance from the lower plate. And so we can integrate this and we end up with sigma over epsilon naught, and then we've got r d0. So this is equal to sigma d over epsilon naught. And sigma in this case is just the charge density. So this is equal to qd over a epsilon naught, because sigma is q over a. Okay, so this tells us that the capacitance then is equal to Q divided by the voltage, which is QD over A epsilon naught. Those will cancel, and this will equal A epsilon naught over D. So that's how we can calculate the capacitance of a parallel plate capacitors. Hopefully you remember from Physics 1B how to calculate the capacitance for some other arrangements too, such as two concentric spheres. Okay, so now let's think about energy with capacitors and how much energy we need to charge up a capacitor. So initially we have our capacitor plates like this, completely uncharged, and so when they're completely uncharged there is no electric field in between them here. But then what we're going to do is we're going to start moving, well, technically we usually move electrons, but we're going to move charges, negative charges from here up here, so that this becomes positive and this becomes negative. And then as this becomes more positive and this becomes more negative, we get a stronger and stronger electric field in here. And so we need to do more and more work to overcome this electric field to move the charge from the lower plate to the upper plate. Okay, so just remembering back to when we were learning about work, we said that the work done was equal to the charge times the voltage. That was how much work we had to do to move this charge Q through some potential difference V. So what we're going to consider now is a point in this process that we were just discussing, where the upper plate has a charge plus Q, the lower plate has a charge minus Q, and we're going to move a little increment of charge up here, and that little increment of charge is going to be dq. So we can say, well, the work that we need to do to move this little increment of charge dq is equal to dq times the potential difference between these two. And we've said that the potential difference, well, we can see from this equation that the potential difference is equal to Q divided by C. So we can write that as Q over C. And what we want to do is to work out the total amount of work that we have to do to charge it up to plus Q and minus Q. So in order to do that, we are going to integrate both of these, and we're going to integrate the charge from 0 to Q, and we're going to integrate the work from 0 to, we'll call the total amount of work W. So this, we can write, this side is just W, and then we're integrating this. And you can see when we integrate this, we end up with Q squared on 2C, and we will substitute in 0 and Q. And so this is equal to Q squared on 2C. So that's how we can calculate the amount of work done. That's in terms of Q. If we don't want it in terms of Q, the charge, we could use this expression here to replace, we can replace Q with C times V. So we could also say that this is equal to CV squared on 2C, which is equal to CV squared on 2. So those are a couple of ways that we can write down how much work we need to do to charge up a capacitor. Hopefully you remember doing a bit of that in Physics 1B.